certifications and hoops you've got to jump through. So those are important design decisions that have to be made early on.
This process is very similar to the software process in that you gather the requirements for the project, figure out what's available. In software, it's libraries. In hardware, it's ICs or sub-assemblies that you have already completed. Design it, put it together, test and refine, sometimes an iterative process. If you see a circuit board that says rev and then has a number other than 0 on it, they've redesigned that one at least once. Usually they'll have prototype revision numbers before they actually get to a release, because nobody wants to open something up and find out that it's the 100th design that they went through before they got one that worked.
Now, after they've got the hardware assembled, there's hardware and software integration, and then testing and refining the design. When you're selecting your chips, the architecture is fairly important. Do you need...
There, I'll take this over.
Do you need fixed point arithmetic? Do you need floating point? How fast does it need to be able to compute? How much memory do you need to store your application? Is it going to be need a lot of RAM, or just because some of these micros only have 2K of RAM, and others can have up to a meg of RAM depending on your chip selections, and whether you want to go with off-board RAM and flash to extend that. And that also, the cost requirement would factor into that. I/O, what sort of communication protocols do you need? Are you going to be talking to other off-chip I/O devices via SPI bus or I2C, or are you going to have serial or AirInc or whatever? So that also determines what chip you select. A lot of the embedded chip these days have a system-on-a-chip architecture. Now, the way that works is they have a CPU core, which is the core which every chip in that processor family will use. And each processor in the family shares the same instruction set. Now, in addition to that core, they'll have like a unified bus which connects all the on-chip peripherals. And that's not so important from a software side, but they'll have multiple like CAN modules or RS-232 or SPI or PWM for doing pulse width modulated signals, or parallel ports, lots of GPIOs. So you've got to figure out what your I/O requirements are from your microprocessor when you're selecting a chip.
All these peripherals are built into the chip, and so the lower end members of the family will have the same core but may not have the same peripherals. For example, where a high-end member of the family might have 16 data lines in 2 ports of 8 bits each, pulse width modulation for analog output, and a real-time clock with a watchdog timer so that if the code crashes, the chip can be reset. But a lower-end member of the family might drop one of the ports and perhaps have fewer counters or lose the watchdog functionality. It just means that they won't be putting those on the silicon, and they'll sell the chip for less money. But it will still be able to run the same code as long as the code doesn't depend on having the resources of the better members of the family.
Out of the embedded architectures that you have to choose from, PowerPC is generally going to be a 32-bit architecture, as well as ARM, I think, comes in 16 and 32-bit variants.
ARM comes in a whole bunch of flavors and is very common. It originally, I believe, was in the BBC Archimedes computer way back in the day, but nowadays is used as an embedded chip. There are versions of Linux that target ARM, and it's usually used basically anything that's very high power but not quite requiring the full power of an entire PC.
Actually, it would be low power requirements, but high computational throughput.
I should clarify. Power in terms of computational power,
MIPS,
not energy consumption.
But the other unique thing about an ARM architecture is ARM is the only one that the people who draw out the ARM specifications don't actually manufacture any chips. So you'll find that you'll have a wide variety of ARM chips all manufactured by different people, because the people who develop the specifications don't manufacture them themselves. x86 is not really that common in embedded applications unless you're throwing a whole lot of computing power at it. It's usually overkill for just about anything you'd want to do.
Sometimes shows up in factory controllers, though. The PC104 architecture is a specification for a very small type of embedded board. It's a full computer about the size of a sandwich. They're available in x86 as well as PowerPC, ARM, a variety of other architectures. The last two architectures on here, PIC and AVR, are kind of very low-level microcontrollers. I have a few in here. They're very simple hobbyist-level controllers. These ones,
the HC9S08 also falls into that because that's another 8-bit chip. The register width is another factor because they still make 4-bit chips for very simple applications. I mean, that's like what a CD player will use with a DSP chip, and the code will be mostly assembly, but very compact and very low
power consumption.
Yeah.
These chips have 16 megs of, no, 16K, excuse me, whole different order of magnitude, of on-chip flash and a 16 megahertz clock speed. They cost about $4 each, which is interesting when you consider that 20 years ago, within living memory, the computational power that I'm holding in my hand would have taken up this room and cost thousands of dollars, and also made it too hot for all of us to be here.
Another thing to note is all of these chips use a system-on-a-chip architecture, and if you're not using a specific peripheral, you can use the memory-mapped registers to turn it off and use its pins as GPIOs. And some of the older PICs only have GPIO ports, so it'll be separated into like a port A, B, and C, where A will be the addresses, and then B and C will be combined into data lines for accessing and executing instructions from off-chip storage. Now, when you're designing your own project, you can usually start looking for evaluation or prototype boards. And they can be as cheap as $20 to $50 or as much as $500 to several $1,000s. And basically what that gives you is a chip, a crystal, a power supply that's well engineered, and breakout connectors for every pin on the chip. And usually a prototyping space like a solderless or soldered breadboard, so you can start building things on there without having to do much groundwork. So for a software person like me, it's very easy to stick a couple LEDs in the breadboard or maybe a Ethernet chip and connect up the SPI bus and build up the connector for the RJ45 and see if it'll work. Some of the prototyping boards have RJ45 already on there, a couple serial ports. It's a very diverse market, but that's where you'd start so that you can start developing software while your more hardware-inclined friend would be developing the hardware with you, or you're learning how to design your own hardware to manufacture.
The one downside of the development boards is that they tend to have the highest end member of that chip family on them to give you the full experience, as it were, with all the ports, all the on-chip peripherals, all the things that that family can possibly do. When you move to a production environment, then you end up with you may end up with a restricted version of that chip for cost reasons. So it's good to keep the eventual target in mind when doing the development. For a hobbyist, that's not as big a deal because any chip, hobbyists tend to prefer a chip that they can buy in single quantities. And if you can buy a chip, the highest level chip in single quantities, it may not be that expensive, and so the evaluation board may be sufficient, and using all the abilities of that chip may not be a problem later on.
The next thing that may influence your chip selection is your tool chain. There's free proprietary tool chains available like MetroWorks, which this speaker badge uses. or you can use GNU tools to build your own cross-compiler for whatever platform you're on, to whatever platform you're on, if that version of GCC can actually build a cross-compiler without errors on your platform. It's usually such a pain to build your own cross-compiler and libc that once you do get one, you immediately put your binaries into source control and freeze it for the entirety of your development unless you have a very, very good reason to change it.
When we gave this talk at DEF CON, I was approached after the talk by a gentleman who develops for NetBSD, who said that the NetBSD ports collection cross-compilers may be considerably easier to use than the Linux ones. I don't have any experience in that area as I'm a Linux user, not a NetBSD user, but considering that NetBSD has been ported to basically anything capable of running computer code, I tend to believe him.
Yeah, I mostly work with proprietary tool chains because that's what my employer forces me to do. I've been trying to preach the wisdom of using
spread the word.
Free tool chains that will always be available. Because if your proprietary tool vendor decides, oh, we don't want to upgrade this to Vista, and then Microsoft says, well, we're not going to support XP anymore, and your specific tool that you've been using for a device which has been in the field for 15 years no longer is able to work on a system which is secure, assuming XP was secure, then you're SOL because all of a sudden you don't have a tool that will work on your operating system. Additionally, another thing is licensing. Sometimes a company will go out of business and their licenses will be on internal timers, and if they're not around to renew it, you're also out of luck.
Another point is that as a hobbyist, you may not want to be constantly changing what architecture you use, and therefore will want to pick something that has a good future ahead of it. This can be a problem if the company decides to end-of-life that chip or family and end support for its compiler as well, because your part may become increasingly difficult to get, the compiler may be lost due to a hard drive crash or whatever, and then you will have to pick up a whole new architecture.
The next decision you have to make is going to be what structure your software needs to have. Is it adequate to do a simple while loop that's going to start at the top, go straight down, and execute each task, maybe the same task a couple times to have it execute more frequently than other tasks in that loop and then start over at the top? And that's what's known as a bareboard zap, because there's no scheduler, there's no operating system, there's no drivers or anything except for what you write yourself. Or you could have a while loop which does round robin based on timers, or some more sophisticated things would be like a real-time OS. Now, what a real-time OS's purpose is to schedule to meet deadlines, and there's a couple types of deadlines. You might have soft deadlines or hard deadlines, depending on your application. As I mentioned before, in avionics, if you have to complete a task every 5 milliseconds to update a display, which, let's say, a traffic collision avoidance system, and you miss those deadlines, and you're displaying stale data, you can see how that might be a problem. Having old data on the display, so you think the plane is here, but really it's here, can cause a lot of things. So the way you get around this is with a real-time OS. And what that will do is it'll preemptively schedule. So it'll stop whatever it's working on and to meet specific deadlines that are critical. So it schedules tasks based on priorities, distance from deadlines, and things of that nature. It all depends on what your needs are for that. You can also use embedded Linux. Routers will typically use embedded Linux or VxWorks.
Embedded real-time operating systems aren't just for aircraft control. They're also useful in applications that are timing sensitive, such as home-built CNC machines. there's a kind of a community online of people who are building computer-controlled machines for building other things. That is, say, routers that are controlled by computers or saws that are controlled by computers in order to machine pieces of material. Those tend to use a real-time OS because it's important that